All right, in this video, I will be plotting some sample data collected for some Energizer batteries where we varied the resistance in an external circuit. So as we decreased the resistance, the current drawn from the battery increased, and we measured the voltage with a voltmeter connected across the terminal ends of the battery. And so you can see from the data that we definitely lost some volts there. That's a result of the internal resistance in the battery, which we're going to determine by plotting the data on the graph and then finding the slope of the best fit line. Because theory suggests the terminal PD, V, equals the EMF E minus the lost volts, which is the product of the current times the internal resistance. We can plot a graph of voltage against current, and the slope will be the resistance. And so just sort of rewriting the equation for terminal PD like this, y equals mx plus b, we know that the slope of our best fit line is going to equal the internal resistance of the battery. So we want to plot voltage in volts on the y-axis against current in amps on the x-axis. And always make sure to clearly label your axes. All right, so the x coordinates range from 0 to 0.0125. And so I kind of think about it like, all right, I want this, all the way over here to maybe be like 0.13. So what's half of like 13? 6.5 would be about here. And so it's like 1, 2, 3, 4, 5. No, there we go. 2, 4, 6, 8, 10, 12. That'll do it. And so if I sort of say each one of these big squares here is going to be 2, but not, really 2, but like 0.02. So it'd be 0.02, 4, 6, 0.08, 0.01, 0.12. That's more than halfway. And so if I say, well, this square here is 0.02, and there's 10 little squares between 0 and 0.02, then each square is 0.002, right? 0.002, 004, 006, 008, 01, and then double that, 0.02. It's like every sort of 5 squares is 0.01. And that's kind of nice because, well, actually, what's my first data point? Is 1 milliamp, so it's 0.001. .02. Oh, no, I've done this wrong, right? I need this to be 0.002. Because this is already higher than my first, or than my greatest data point, right? I need 0.012. So I just was off by a factor of 10. So this one is 0.001. This will be 0.002. 0.003, 004, 005, 006, 007, 008, 009, 01. That's what we want. So that one right there is going to be 0.01. 003, 004, 005, 006. And so the scale is every little square is 2 by 10 to the negative 4, or 0.0002. Okay, let me kind of, I'll just talk because I switched it to a different camera for each one of these. So I'm going to zoom in for the e-learning students and for the YouTube video, and then I'm going to try to do the same thing here, but it's going to be slightly sort of off-centered for one of you. All right. So here, this is the scale that I've sort of chosen here. See, every 5 squares is 0.001, which means each one of these lines is 0.0002. 0002, 0004, 0006, 0008, 001, and so on. So it's a really tiny scale. So it's like really this is just like 1, 2, 3, 4, 5, you know, and so on. But there's this, it's like this is 1, and then I could write, you know, here that this is times 10 to the negative 3. And you kind of scale your axis like this. So you say like, I don't want to write all these tiny numbers. I know that everything is 1, and then I'm doing it times 10 to the negative 3 amps. And so you can kind of write, if you wanted to, and this is just a suggestion, that's not a requirement, but if you prefer kind of, oh, I like that a little bit better, that's a little bit sort of cleaner here, you could say, I'm reporting my X quantities in its current, and it's measured in times 10 to the negative 3 amps. Okay, you sort of account for the fact that I'm just going to plot 1, 2, 3, 4, 5, not 0.001. Everything is times 10 to the negative 3. It's like milliamps, right? Like you're saying, hey, I'm plotting milliamps, but this is like a way to sort of also, you know, sort of report that. Again, if you do that and you do the calculation with these numbers, 1 or 2 or 3, you have to remember it's really times 10 to the negative 3, right? Because the unit is amps. Okay, so again, it's just like you prefer to not have to convert, or, you know, and work with sort of smaller numbers, or work with more friendlier numbers, but you got to sort of convert it at the end. So it's up to you. So 0.005, 006, this would be 0.007, 0.008, 009, 01, 0.011, 0.012, 0.013. So you basically say like, okay, I've got 12 and a half, and I need to get up to 13. And it has to be more than half of the page. And that certainly is, right? 13 here. If we're here, it'd be more than half, right? So here is well more than half of the page. And I'm actually going to just keep it like this, current in amps. I don't mind working with sort of these values like this, even though they're really tiny. You can't really see them right now, right? And so let me kind of zoom in here for the, all right. And so this was just a suggestion, sort of you could write, you know, 1 and then include the times 10 to the negative 3 sort of in how you labeled your axis. I'm just going to leave it as current in amps, and I'm going to plot these values 0.001, 002, and so on. Now, the old y-axis. We certainly want to break the graph, okay? Because we don't want to plot all the values from 0 to 3, or we don't want to include them in our plot, because it just be, you know, empty space. Our data ranges from 3.07 down to 3.03. So if I sort of call this first sort of square here 3.03, then I know sort of my last data point is going to be sort of down here. Okay, and then I want 3.07 to be way up here. Right, that's the whole point. I want to spread this data out so that it occupies most of the page. So if I go 3.03, 04, 05, 06, 07, then I've got all my data right here, and I'm making every sort of 10 squares 0.01. Well, that's not even more than half the page, so I could just double the scale. So instead of going up to 3.04 here, it goes up to 3.035, and then 3.04. So it's like every 2 big squares, every 20 of these little squares is going up by 0.01. So it would be that'd be 3.04, 3.05, 3.06, 3.07. Okay, that's pretty good, right? That's more than half. So 3.07 would be up here if I make a scale where like this one is 3.035, 3.04, 3.045, 3.05, 3.055, 3.06, 3.065, 3.0. All right, see that? That's the hard thing to sort of do when it's data like this. All right, is to actually choose a scale like this for graph. So see, it goes up by 5. And you can always sort of say, well, what is each one of these little squares then? Because that's helpful to keep in mind when you plot the data, because we're making judgments about like, where does exactly, this point fall? Maybe not so much with this data set, but it's always helpful to kind of know, like I did here on the x-axis, every single square on the x-axis is 2 by 10 to the negative 4 amps, right? 0.0002. That's what a square is on the x-axis. Every square on the y-axis here is equal to, well, if it takes 10 squares to increase 0.005, 0.005 divided by 10 means every square here is 5 by 10 to the negative 4. Okay, every time I increase, it's going up by 0.0005. So this would be like 3.0325 in between. The 5 here would be, because it's 3.035, so 3.0325 would be this one. Kind of like that. You needed that level of precision. All right. That's kind of what we're saying. Every square is 0.0005, so it's going up 3.0300, 3.03005, 3.031, 3.0315, 3.032, 3.0325, and so on. And it starts to hurt your brain a little bit. That's okay. Good mental exercise. All right. Even though it took a long time to get a good set of scaled axes, it's worth it, okay? Because then the data plotting is so much easier. Like if you just take the time up front to get a nice set of scaled axes, and the data sort of falls, and you don't have to sort of struggle with the plotting too much. All right, 0, 3.07, my first data point is up here. Now I'm plotting 0.001, and it's 3.06, and so it's sort of exactly there. 0.002 was 3.05, so it's like here. 0.003 was also 3.05, so it's there. 3.006 was 3.04, so it dropped down to here. 0.01, we had 3.03, and 0.125 would be 2 points would be right here, and it's also 2.3. So remember, we sort of discussed that our data would kind of be like a little staircase like that, where some of the y-coordinates would be the same. And so here we can sort of draw a trend line through that, right? Like there's definitely a negative trend. It's, going to occupy this. It does resemble sort of what I said it should look like, but it really does kind of reveal like maybe we needed a more precise voltmeter, right? Like it could only measure it out to the hundredths place. And so like, it'd be good to kind of see maybe some intermediate values, but this is all right. And so kind of like that seems like maybe a good trend, except for then it's like, well, we're just starting these points up here, right? So if we try to like maybe get that, I really kind of want the EMF to be on my line. In other words, I want my y-intercept to be this, because I know like that's a data point. Okay, but maybe the trend suggests the EMF isn't that, except for we know it is because we measured it. So I'm going to commit to this one. Okay? Now, a lot of these points are below my line. So that's not really maybe the best line that I could have drawn. That's a deficit line. You could maybe say, well, what if it's sort of like this? What if the curve of linear trend? It's not linear at all. I think it's really an artifact of like how it sort of plateaus like this and sort of kind of stretches the data out like that. Yeah, it's really maybe not the best data collected. I should just scrap the whole lab and start over. You know, you could draw a line sort of like this, but then you're sort of discarding these points. Okay. For the purposes of my analysis, I really want to actually just, I mean, it's not too bad for me to just do 2 slope calculations. And I kind of want to see like, well, if that's my best fit line, what would I get? And if that's my best fit line, what would I get? And maybe I'm just going to record my answer as a range of values. I can do that because I'm a doctor. Okay. But you could do it also as a student of science saying, this seems more reasonable to me. Like, yeah, I don't really like the way that I'm not really accounting for these. So I'm going to draw 2 best fit lines. And maybe it's the line in between, or maybe it's like there's a range of, I don't know. It's really up to you to kind of decide how do you want to analyze this data set. So now I'm going to scour my plot. And so my first sort of line here, I see a good data point right there. Not a data point, rather, a point on the best fit line that is not a data point. That's what I'm looking for. And I want to try to find 2 points that are, again, more than halfway of the page apart from each other so that the hypotenuse, if I draw like a right triangle, the hypotenuse on my best fit line is more than half the page. That's the strategy, that's the goal. Point 0.0026, 3.06. Okay. And for this one, 0.01. 3.0335, right? This would be 3.033035. Okay. So I've got some coordinates there that probably you can't see unless you've got really, really good eyes. And I'm going to find 2 points like outside. Zero, 0.0048. And this one right here would be 3.0375. 3.0375. This one is 0.002. Three point zero six 0.5055 555. This is where it gets confusing. All right. 5.06. So it's going up by 0.0005. So if we added 3.055, 3.056. And again, sort of working with such a small scale, right? That's why you can sort of use the other strategies, like make the numbers bigger and, you know, deal with the conversion at the end. So my first best fit line has a calculation of 3.0335 minus 3.06 over 0.01 minus 0.0026. That's one value of R I'm going to import. And then another value, and it's really negative R, so I'll take the negative of it. And then the other one I'm going to report is going to be 3.0375 minus 3.056 over 0.0048 minus 0.002. Negative 0.0265 is the difference here. .0074. Yeah, 3.58 ohms, that seems like a lot. And for this one, .0185. All right, so I get a range of like between 3.58 and 6.61 ohms for internal resistance. Okay, between 3.58 and 6.6. To me, that seems really, really high. Okay. In other words, I don't really think that's the internal resistance of a Energizer battery. I think that there's something else in the lab work that we need to sort of consider here, but we'll save that for another day. And it's fine to sort of, you just trust the data. In other words, once we get a conclusion, we say, well, did we make any mistake? Like there was no mistake in my calculation. I didn't misplot anything. Those are really the numbers. The numbers don't lie. Sometimes the interpretation of the data can be misleading. And other times there's some systematic error or there's something sort of in the analysis that we're not accounting for. It just seems like these are really high values of internal resistance that a battery wouldn't really have that much internal resistance. Okay. But I wouldn't stop that from reporting those as my conclusion, my claim. Hey, based on my evidence, see the evidence, theory suggests this, and because I apply that, and then you can maybe in your reasoning try to say something like, perhaps because the sensitivity of our voltmeter wasn't accurate, sort of the staggered nature of this data made it so that the best fit line, it didn't really lead to the best conclusion. Maybe we needed more data points. Maybe we should have really tried to find some data sort of in between. And so you can critique the lab. That's actually one of the best things that you can do as a scholar, sort of studying science, to say, how would I improve this lab? What could I have sort of done differently? And as you learn more about sort of different instrumentation that's available, have sort of more tools in your toolbox to kind of work with that. So I would report sort of the internal, according to the data, you can always sort of qualify your statements like that. According to the data collected, and according to my analysis, I claim the internal resistance of the Energizer battery is somewhere between, I would say maybe, 3 and 6, but see, that's a big uncertainty, right? Like, it's as much as plus or minus 3. So maybe it's as low as 0, right? So it's like, it's between 3 and 6, so plus give or take 3. It's this plus or minus 3, maybe it's 0, maybe it's 6, maybe that's sort of. What you can really do is average these and then do plus or minus sort of the range. And so the way that we would actually calculate that, 6.61 minus 3.58, there's a range of 3.03, half the range, 1.5. So 3.58 plus 6.61 divided by 2. So if you average these, you get right about 5.1 ohms. And so you maybe say, well, 5.1 ohms, plus or minus 3. Maybe as low as 1, maybe kind of that. And again, I don't even think that's right. I think it's a smaller fraction.